Hello, everyone, and welcome to the Control Engineering webcast, Enhancing Mineral Processing with AI, Digital Twins, and Computer Vision, sponsored by Honeywell. I'm your moderator, Gary Cohen. Very happy to join you today on behalf of Control Engineering. Before we dive into the main content of the presentation, I'll give you a few moments to review Honeywell's Safe Harbor statement. Thank you. And now we get to the good part where I get to introduce our wonderful speakers. Cesar Bravo is the AI Solutions Director at Honeywell. He has more than 24 years of experience setting the strategy and overseeing research, development, and implementation of digital solutions for process industries. He's performed various leadership roles in research and development, product management, and consulting at industry-leading oil and gas services and operator companies. Cesar is a recognized thought leader and author of more than 30 technical papers about digital transformation, the digital oil field, and the application of artificial intelligence and optimization methods in industrial production processes. Rodrigo Toro is an expert in automatic control with a Master of Science degree from the Polytechnic University of Catalonia in Barcelona, Spain. He also holds a Bachelor of Science degree in Electronic Engineering from the Federico Santa Maria Technical University in Valparaiso, Chile. During his 16 years at Honeywell, he's been working on topics such as dynamic systems modeling, identification and simulation, optimal predictive control, and data science. Rodrigo has extensive experience in data-driven solutions and project management. As a data science manager at Honeywell Chile SA, he led a diverse team of engineers, data scientists, and developers to deliver advanced process control, simulation, data science, advanced analytics, and information application projects. Before I hand the floor over to Rodrigo, I want to remind everyone attending that if you do have a question for our presenters, you can ask those questions in the comment section throughout today's presentation. All right, thank you so much for joining us, gentlemen. Rodrigo, I'll hand things over to you to get things started.
Thank you, Gary. Well, this is today's agenda, so let's begin. Mining industry is under a lot of pressure. Social expectation, decarbonization goals, and the demand for higher productivity, and all this is converging now. So we're also living a bit of a big shift from manual to autonomous, from reactive to predictive. The question is no longer if we transform, but how quickly we can do it. Our vision is very clear. We want to move from control to autonomy. And to realize this, we are aligning process control, asset reliability, and human performance under one integrated strategy. Well, advanced process control is still central, but today we want to combine it with artificial intelligence, machine learning, data-driven models, and first principle simulation. And we are designing operations that are not only efficient, but intelligent and adaptive. And here's where the shift happens. Traditionally, digital systems try to catch up with the physical plant, and we want to reverse that. With simulation tools like Unisim and also using machine learning models with Halo recommendations with the Smart APC, we let the digital plant lead. And the result is that every action in the field is first optimized in the digital world. So we simulate, we predict, we optimize, and then we execute, delivering measurable outcomes. Honeywell's portfolio support the full mining value chain across process, people, and assets. We bring together control systems, process optimization, asset reliability, industrial software, and safety systems to deliver a fully integrated operation. And now Cesar will share with us the Honeywell vision for industrial artificial intelligence.
Thank you very much, Rodrigo. As Rodrigo mentioned in the previous slide, Honeywell has a comprehensive solution portfolio intended to enable intelligent autonomous operations for process industries, including, of course, mining, metals, and minerals industry. Our portfolio is infused with AI across the board and support the entire value chain, from field operations to the control room to advanced application to support enterprise and business decisions. We implement AI solutions with the intention of augmenting the capacity of the people, the process, and the asset. And that is what I'm going to explain in the next slides. What I want to do now is presenting some examples of applications that are AI enabled that provides value for the field operator, for the control room operator, and for the engineer and managers at the enterprise level. Let's start with the field operation, and we're going to talk about one particular application that is called Field PKS, Field Process Knowledge System. Honeywell Field PKS is an advanced solution intended to support the work of the field operator and the field maintenance technician. Usually, the operator, the technician, needs to go to the floor plant every day to perform what is called a round. They need to go and check on the status of the equipment, check on the status of the process, identify hazardous or out of normal conditions, and report that back to the supervisor. The supervisor needs to take this information and plan the job for the day and assign that job, that can be a maintenance procedure or an operational procedure, and assign that to the resources available in the floor plant. But to do this, both the operator and the supervisor requires to access information from many sources. For example, they need to access ERP systems to see what is the plan for the maintenance, to check on spare parts, and check on inventory. They need to access the real-time system to understand what is the status of the process. They need to go to several documents to look OEM documentation, to look for operational and safety procedures, etc., and go to many other OT systems that are related with maintenance, and performance, process performance, etc. All of this usually is done in a very manual and sometimes tedious way, right? And takes time. Right? So usually an average of the maintenance tasks or the operational tasks that happen in the floor plant can be maybe days. What we do with Field PKS is we integrate all the relevant information for decision making at the field operation point of view. And we not only integrate that information, we do this in an intelligent way. We do this in context. Right? So we contextualize the information and we provide this information in natural language to the operator. How? Using Gen AI. So we use Gen AI technology to process the information, to contextualize, so the operator can interact with the application in natural language, doing intelligent search and getting the information readily available. Right? And we're going to see that in a moment, how that works. Let me explain you how Field PKS work with an example. So let's say that we have a field maintenance technician doing a daily round. Right? So the technician is going to go to the field and do an observation across the board of all the assets that are assigned to his round. And let's say that this technician identify an issue, identify that is an equipment with a potential failure, right? So what the technician is going to do is going to capture an observation and is going to set that observation, to insert that observation in the Field PKS system. But to do that, to really capture the valuable information for decision making, the field maintenance operator can go and check information about the OEM of that particular equipment, can check information about the previous failures that the equipment has, the previous maintenance and the last maintenance that the equipment has had. So with all that context, then the field maintenance technician can raise the observation and put all the relevant information for the particular situation, including pictures, including videos, including voice notes, audio, and additional documentation that he can found in the field PKS. So all this information now contextualized is going to go to the supervisor in real time. The supervisor at the office is going to look about this, going to look at this observation, and is going to look all the contextual information, and then is going to plan a job based on that. Actually, the system is going to help the operator to create the job pack related to this observation. Once the job pack is created, that is going to go back to the field. So now the system is going to look what are the available resources that are there in the field that day, and with the required skill to perform the job that has been planned. And based on that information, the system is going to assign the task. Information that now the job pack goes to the right resource, that can be the same technician as before, or somebody different, or maybe many other resources. And then, this job pack is going to be assigned, and it's going to provide it with all the contextual information that the field operators need to perform the job. Now, the field operator take the job, look at the description of the job pack, is going to look at the contextual information that can be, fit by information about the equipment, again, about the operational procedure that needs to be followed, step-by-step guidance of what to do, right? Even the evidence in the fashion of picture, videos, voice notes, etc. So this operator can perform effectively the job that has been assigned. Operator goes, perform the job, and execute efficiently. And then once the job is completed, the confirmation is going to send back to the supervisor to review the job and close the request. All this process that I just described, if the operator and the supervisor don't have field PKS, can take several days. Why? Because just to get the observation, the operator needs to, the field technician needs to call several times to different persons, to the maintenance supervisor, to the control operator, just to make sure that has all the information required. Field PKS is providing all of that integrated in one single platform. Then for the supervisor to plan the job pack, again, needs to call many people, look for information in different systems, etc., and so on. So there is a very manual and tedious job. With field PKS, all the information is integrated, is available, and not only available, for search, but it's available in a fashion that the operator can interact with the system in natural language. So it's very easy to get the information. And more than that, the system automatically generates the job pack, so can automate the workflows and assign the resources. So now, what the operator and supervisor have is a companion that is automating all that manual work that have been done traditionally, in the past, and now is reducing the time to make the decisions to execute the job, and is giving all the contextual information to perform the job in an efficient, repeatable, and consistent way. Now let's move from the field to the control room. Let's go to the second level of the industrial AI solutions. And we are going to talk about a solution that is called Halo Operation Assistant, that is intended to augment the capacity of the control operator at the control room. Halo Operation Assistant is the next generation of control room operations UX. Right? What we are doing is augmenting the DCS capacity, providing intelligence that support the work of the control operators. And we have several components here. So let me try to explain. So here we have a traditional faceplate in let's say mining environment, right? So you have all the equipment here with the level of the variables, the alarms, etc. But then we start looking at different other components that are enriching this faceplate. The first one is the watch list. So the watch list is intended to present the operator with the most important variables based on the condition of the process. What that means that the system is going to analyze what is the status of the process, what is the criticality of the variables, and is going to present the variables that are more critical for the operator. Of course, the operator can select some variables that can keep an eye on, but the system by itself is going to present what are the critical variables so the operator can be aware of what is happening. The second element is a very interesting one. It's what we call look ahead runway. The runway is intended to present not only what is happening now, what are the alarms that are happening now, but what is going to happen in the future. So we present a horizon of time that is going to bring predictions about what is going to happen. Right? So we can present scheduled events, plans, so for example, plant maintenance. You can present some operational procedures that are going to be performed. We can use APC to predict the behavior of the process and try to warn the operator about something that is going to happen 1 hour, 2 hours ahead. And we can also use machine learning models to do prediction. We can detect patterns and try to warn the operator that something in the future is going to happen. So you better take care of some action that needs to be performed. So this is very powerful because now you are giving proactivity to the operator, and now you are avoiding to get to the alarm level, right, by providing these predictions. And that is what is called look ahead runway. Now, let's say that one alarm happened. So an operational event occurs. One variable goes out of the operating envelope, reach one of the limits, then the alarm is triggered. We have a solution that supports the operator, guide the operator on what to do when that alarm happens. Right? So, and that is what we call alarm guidance, intelligent alarm guidance, and we're going to see an example in a moment. Right? It's guiding the operator. So, if this event happens, this is the path that you need to follow. Right? And that is what we call advice here in the screen. And finally, the last element is what we call electronic work instruction. Usually in the plant operations in the industrial processes, there are what is called standard operating procedure. But these procedures are usually in a document, in a PDF, for example, or in a printed document. So every time that something happens, the operator needs to go to the repository and look for the procedure. Of course, if you have an experienced operator, that operator most probably already knows the procedure. But what happens is now you have a lot of early career operators that are not that familiar with those procedures and now need to go and manually look for that procedure. What we do with Halo Operation Assistant is we provide those procedures in a digital way. We digitalize the standard operating procedure and present step-by-step guidance to the operator of what to do related to specific operational events. You see, now what we're providing is an enriched context to the operator so that he or she can know what to do when an operational event happens. And let's go deep in how this works. So here we have what we call the Smart Alarm Management screen. So I was mentioning before, so that when an alarm happens, usually what is going to happen in the system is that the alarm is triggered, is presented in the alarm panel, right? And usually you are going to have some information regarding what is the behavior of the alarm. Here, for example, we have that the level of one of the variables is increasing, right? And has reached the high level, right? Now it's getting out of the operating envelope, right? So usually what you have is maybe the alarm, the description of the alarm, and the trend, right? So the operator can look what happened and then decide what to do. Now with the Halo Operation Assistant and with the Smart Alarm Management functionality, we are not only going to present what's happened with the variable. The system is going to look back in previous occurrences of this particular event, this particular alarm, and it's going to bring those previous occurrences to present that context to the operator. For example, you can see some purple lines here. So here what the system is doing is telling the operator is, hey, this event has happened in the past, and in this occasion, in a couple of occasions, the operator took some action that brought the system back to the operation envelope. But in some other occasion, maybe 3 of them, the system continued degrading. So with this gives some context of, maybe there are some paths that are more effective than others. The system also presents some variables that are related to this particular one. For example, this is a level that is increasing. Maybe I'm interested to see what is the RPM of a pump that is upstream in the process. I want to see what is the feed, right? The feed flow that I have in this particular equipment, etc. But the most interesting thing is what is in the right side of the screen. Here, what we do is that the system is going to look back. It's going to analyze what is happening, it's going to present a potential cause, but more importantly, it's going to recommend actions. And from where that recommendation are coming, the system is going to look back in the log of when this alarm happened, what the operator did. It's going to look in the experience of the operators. I'm going to see, okay, in the past this happened and the operator took this action, and then that action brought the system back to the operating envelope. And that is going to be presented to the operator that is dealing with the situation now. So let's say that you have an early career operator, 1-2 years in the plant. It's the middle of the night. There is not a experienced operator in the control room in that time, and something happened. The operator is the first time that this early career operator is facing this alarm. If you don't have Halo Operation Assistant, most probably what the operator needs to do is call the expert that might be sleeping or not available, and then ask what to do. Or maybe go and look into the documentation and try to figure out what to do. With the Halo Operation Assistant, what is going to happen is that the recommendation is going to be there. The system is going to tell, hey, this happened in the past, and this is the action that was taken that brought the system back to the desired behavior, the desired performance. That's very powerful, but it's not easy to do because you need to look back and make sense of many data sources to present that recommendation in a very clear and consistent way. And I'm going to show you how that works in the background. So the way how Halo Operation Assistant works in the background is represented in this slide. So what the system does is integrating information from primarily the real-time system, from the DCS, the historian, etc., to understand what is the state of the process, right? And understand when an alarm happened and what is the trend of the variables, etc. Then as well brings information about events and alarm logs. So look into the logs to associate whatever alarm is happening with some logs that are recorded in the system. We also integrate information about the process flow, so PNIDs and some other diagrams that can make sense about what is happening in the process, as well as standard operating procedures, safety guidelines, etc., any procedure that is documented or recorded in the system. And we also integrate information from other systems like alarm management system, production management system, etc. We take all that information and we integrate that in context using knowledge graph. And what the knowledge graph is going to do is going to make sense of the information, and it's going to associate the process with the alarm, with the values, with the actions, right? So we are going to create what is called a lineage. When an alarm happens, so it's going to be a relationship between the variables, the value of the event, the alarm, the event, and the action taken in the past, right? All of that in context. Now, having this information in a contextual manner is the first step, but then the information needs to be presented to the operator in natural language, so the operator can understand what is happening or what the recommendation is. So what we do is we use GenAI. We ingest the information from the knowledge graph into a vector database and go to the small language model. So the information is processed and now is presented in natural language to the operator. Now the operator gets the recommendation, is a clear way in natural language and can understand what is the procedure to follow, right? And this, what it does is capturing the experience and the knowledge from previous operators that is recorded in the system but in different data sources in a scattered manner now is contextualized and presented in a very clear and meaningful way to the operator. So these cover the first two levels of the solutions that we have in our portfolio. We started with the field operations with field PKS. Now we went to the control room and presented a solution that is Hello Operation Assistant that augment the capacity of the control operators. Now what Rodrigo is going to do is going to go further in the solution that support the operations. Is going to talk about smart APC. That's a very interesting solution, and some implementation of computer vision. And then it's going to go to the enterprise and business level. So it's going to be a very interesting walk through the solution that we have. Now, Rodrigo, please go ahead.
Thank you, Cesar. Now let's zoom into the technologies that are enabling this transformation. So following the idea of technology infusion, we are enhancing our solutions with machine learning and first principle digital twins. We use this hybrid strategy across advanced process control, asset performance management, and event detection for computer vision. This enables real-time decision-making, especially in challenging processes like flotation and grinding. First of all, every one of our technology infusion projects follows a business case that can be related either to cost reductions or revenue increase. Now I want to share with you 5 use cases where we have infused machine learning and digital twins technologies into our solutions. Let's start with machine learning technology infusion for process optimization. First of all, let's do a short recap of advanced process control. In Honeywell, we use a control strategy called model-based predictive control, or MPC for short. The main idea is to install this supervisory control layer that is multivariable and help us to reduce variability, giving us the chance to operate closer to our constraints in a safe manner, helping us to increase throughput and recovery, reduce energy and water consumption. So what next after APC? We all know that mineral processing is complex because it's hard to measure important properties like ore hardness and ore grade online. And ideally, we should adapt our operational ranges or limits based on variations of those variables. And that's the main idea of Smart APC Supervisor. Use machine learning to adapt the APC applications based on operational modes. So Smart APC Supervisor brings AI closer to real-time decision loops. It integrates machine learning models, AI optimization, clustering-based operational mode detection, and cybersecure execution at the level 3 of your control system architecture. Machine learning recommendations are applied with a translation layer to the APC. So you can keep your control strategy and Smart APC Supervisor, enhance it with AI recommendations. The results speak for themselves. Improved recovery, increased throughput, and a faster return of investment. This is a case where we optimized 2 SAG mill lines that converge into a collective flotation, and the results are incredible. Okay, so this is one of the nicest case that we've implemented, and so far, in this moment, we were using interactive recommendations, so the operator received the recommendation and they have to accept it or reject it. But now we are closing the loop autonomously. Okay, so the first stage can be interactive, and then we can move towards a full autonomous solution. And now let's move forward with a machine learning technology infusion use case for computer vision. Multivariable APC relies heavily on the quality and diversity of the input signals. This is where machine learning plays a crucial role. By infusing new sources of data, such as visual information in this case, into the control loop. Computer vision systems can capture operational features, like the froth behavior, the bubble size, and texture, that are traditionally hard to quantify or only available through offline lab analysis. These systems effectively act as intelligent sensors, transforming visual patterns into real-time numerical data. By integrating this information with APC, we can improve optimization performance. For example, detecting subtle changes in flotation froth or conveyor belt loading can fit predictive models that guide the control actions. Using tools like C++, we generate structured, reliable, and contextual data from industrial-grade cameras. This adds an additional layer of intelligence to the plant, one that's visual, data-driven, and fully integrated. The result is a smarter, more responsive control system, optimized not only by process measurement, but by what we can now see and quantify with computer vision and machine learning. In flotation, visual cues are critical. Bubble size, velocity, froth depths. This used to be estimated manually or sampled offline. We've used machine learning to detect abnormal situations such as sunken flotation cells and froth collapse. With C++, we captured this in real time using industrial-grade vision systems integrated into control loops. And over 600 flotation cells from our customers are already generating benefits from this. Same goes for rock monitoring. Particle size, belt anomalies, and ore characteristics are now visible to our systems before a failure or a stoppage occur. And here we can see capture of our systems, the video feeds, and the information that we are delivering online. And in the upper row, you can see some video feeds from the C+ froth or flotation. We have different regions of interests that can be well configured depending on the shape of the flotation cell, and we can detect events like, for instance, when the froth collapse or when the cell is not overflowing. We also have other parameters like texture and indications of bubble size. In the lower row, you can see some feeds from the C+ rock solution, and we're also investigating or researching some new features. We're actually testing it. For instance, the ore estimation with stereographic cameras. And imagine this. You usually have in the important conveyor belts mass flow with a weightometer, isn't it? And now with this system, you may have a volumetric flow. So mass and volume, that's density. And if you can estimate density in real time, you can open the black box of what's happening inside a SAG mill, for instance, or a ball mill. We can also identify the big rocks that maybe are going through a primary crusher or something like that. And we can detect also belt misalignments. So now let's move forward to another use case where we have infused machine learning technology and digital twins technology into APC. Okay, well, so typical uses of first principle models, um, usually for greenfields, with the OTS or operator training simulators. That's a no-brainer. It can help you dramatically to accelerate your ramp up. And it's a solution that you can use through all the life cycle of your plant. Okay? So simulation is no longer optional. That's the key message with this. With digital twins connected to control systems, we can simulate plant behaviors before the startup, during commissioning, and for operator training. Okay? And this is a use case, as I was saying, for greenfields. This is the case of Anglo American Quellaveco. We did a high fidelity dynamic model for them, and we use it for virtual commissioning. We tested everything with an EPC, with a DCS provider. So our solution in this case was operating with a third-party distributed control system, and we developed an early APC. So only 2 months after the plant startup, they started running in full automatic mode with APC. And also, well, before the startup, of course, we trained the operators not only in the use of the control system, but also in the use of the APC. So that was a key enabler to start operating with APC only after 2 months uh, before the startup. So sorry, after the startup. Okay, so what usually happens after the startup of a greenfield is that the dynamic model that you created for that purpose is not longer realistic. So the plant started, uh, the simulated plant is not exactly the same as the running process, as the real thing. Okay, and and well, that's super challenging because as soon as the plants start, you want to have a simulation that is as close as possible to the real stuff. Okay, and for that reason, we have included in our Unisim solution a hybrid modeler. And when we talk about a hybrid modeler, is that we're mixing the first principle equations that we already have in our processing library with machine learning models. Okay, it can be neural networks, can be whatever Python or scikit-learn or PyTorch library or model structure that you're using. And the main idea is that you are feeding the model with the real inputs or outputs of your plant with your measurements, and you are working like tuning your parameters or even modeling that error to create a model that can be representative of the real process. Okay, so well, this is a new feature. Well, it's been around for a little more than a year, and we've been using it intensively for real-time purposes, so real digital twins here. And one of the use cases here is, for instance, uh, an equipment that it's super common in mineral processing, and it's most of the copper, gold, iron ore concentrator plants are the hydrocyclone batteries or hydrocyclone clusters. So the thing that typically happens here is that it has some very nonlinear behavior. So for instance, every time you open or close a hydrocyclone, it's not the same if you are processing the nominal throughput, or if you're processing under that throughput, or if you are um, with a small number of hydrocyclones or with a high number of hydrocyclones. So usually we include important variables of the classification in our APC. We usually have a control variable that it's the pressure of this hydrocyclone cluster. We we want to maintain the pressure as high as possible to have a good classification, but not higher than that because we can generate big problems with that. And if you are operating with a very low pressure, you will not classify uh, as good as if you were in the higher part of the range. Okay. And we've been actually doing this for more than 2 years. We've been enhancing the MPC, the model-based predictive controllers. The models that we're using in MPC are linear models, very robust, big technology there, but um, in those cases where we were using the pressure as a control variable and the number of hydrocyclones in the cluster as a manipulated variable, that relationship wasn't that good, and we had to retune every time we change um, operational modes. Okay, and for this we have integrated the first principle. Unisim model of a hydrocyclone cluster with the uh, advanced process controller to enhance the models and to have a wider range of operation. Okay, and this is a great case of technology infusion. In this case, digital twin and machine learning into APC. And our APC engineers have reported that they no longer have to retune the controllers every time they change operational modes. There were a lot of wizard rules and magic that we were trying to implement to tackle that. But this solution is way more elegant in this case, and it's been working for a long time now. This is a great case study, and um, lately, we've been working with a product that we launched last year. It's our Honeywell Process Digital Twin, where we are integrating all these technologies. So this is some screenshots of that solution where you can integrate a model, you can integrate that with the APC, you can compare the calculated variables in the model with the reality. You can generate the error, and if you see that there's bigger deviations there, you can report that as an anomaly and start investigating maybe the performance of the process. Um, you can actually operate the model, create what if scenarios. This can run in the cloud or on premise. And you can run also what I've shown, this integration with the advanced process control. Um, Something that is very nice about this is that you will have all the time running a real-time instance of your simulation. It can be integrated with other models, maybe made in Python, um, and well, you can have all those hybrid features. You can run optimization routines, um, but you always will have this real-time simulation running. And every time you want to do, for instance, an optimization or a what-if scenario, you will take a separate instance. You will use a snapshot that could be in the past or can be the current moment. You create a snapshot and you can run a what if scenario and create a report for the operator. So for instance, imagine that um, you maybe are a process engineer and you arrive at your shift and you see that, oh, maybe I'm sending a little too coarse the mineral to the flotation stage. Okay, so the mesh is a little high on the above the high limit. And well, I might have some hypotheses. I can start testing in the real process, but maybe I can run a what if scenario in accelerated time. So I test my hypothesis, or maybe I can program an optimization routine and then I'll get an automatic response or recommendation for that. Then I can check the results and create a report for the operator and tell them, okay, look, we should do this, maybe add some more water, maybe close a hydrocyclone to reduce the mesh that we are sending to the flotation. So we're making decisions based on data, digital first, because we test everything in the digital plant and then we move to the real plant. Okay. Now, I want to move to another dimension of this, that it's asset performance management. And I want to share with you a couple of use cases here. The first one is technology infusion project, where we infused machine learning into a system for early alerts. Okay, so well, the main idea under those early alerts is try to avoid a unplanned shutdown. That's the whole stuff. Every time we have an unplanned shutdown, uh, all the benefits that we get with the APCs, all the benefits that we got with optimization are diminished by this unplanned shutdown. So the main idea of having early alerts is to understand um, situations where you are reaching or you may reach in the near future hard constraints, and that may lead to an unplanned shutdown. Okay, and make some changes in advance. gain some time, buy some time in this case, isn't it, to avoid the unplanned shutdowns. So we have our asset performance management solution. We can deploy it on premise in your control system architecture, in the level 3 usually, um, or it can run in the cloud, or it can be hybrid. Okay, and the main idea of this platform is that it lets you integrate data from wide variety of sources. It can be mobile equipment, it can be fixed equipment, and then you can run performance models or fault models. You can run models as simple as something that you may have in an Excel spreadsheet, and you can integrate that in real time with real-time data. Or it can be a unisim model with high fidelity thermodynamics, particle size distributions, etc. It can be your own model with a Python library, machine learning model, for instance. And you have a workflow and a way to understand what is happening, and with this data structure for the assets, where you can see the asset and fault tree with nice dashboards. And also you can monitor the data in an integrated way. So you are taking tasks that usually were offline duties to an online platform. And also you have workflows to investigate the deviations and to create work orders. Yeah, it can be integrated to your ERP, etc. So it's a great solution. And in this case, we did a project for one of our biggest customers. They were moving from a plant that has two primary crushing plants separated to a bigger but centralized primary crushing plant. So in this case, they were a little concerned because they moved to, well, this sort of redundancy with the two primary crushing plants to a single point, sorry, of failure. Okay, newer plants, new, better equipment, etc., but single point of failure. So we created an early alert system for them that was also integrated with the operator and the reliability engineer. Okay, so the idea was basically if the early alerts were raising concern because it was within the timeline of the shift, it will be presented not only to the reliability engineer but also to the operator. But if it's something that may happen within a month, it will only present it to the reliability engineer because the operator doesn't is taking care of the real time. Okay. Uh, the type of alerts that we implemented were three. Okay. The first two, very simple one. The first one, it's what we call the unforced prediction. So what may happen if you don't change what you're doing? Okay, if you continue operating in this way, this may happen within the next day, month, etc. Okay, it's like an extrapolation. The second one was the most simple one, and limits. Okay, if I violate a limit, I will raise an alert. That's it. And the third one is a little nicer. It fits within the machine learning, let's say, theory, and we are using a variation of the principal component analysis that we developed with the University of Alberta, and it's called the moving mean principal component analysis. So basically, with this type of model, you model the normal operation, not the abnormal operation. You model when the things are happening as you like to. Okay, so we take all the variables that we know that would be important for the model. In this case, um, everything related to the lubrication system, everything related to, well, the conveyor belts, um, upstream, downstream. Okay, all the data most of the data you have. Of course, we do some exploration first. We do a feature analysis. We select the main variables, etc., and we define what variables we're to use for this. And we model the normal operation. And every time we move outside the normal operation, we will create a graphic, a Pareto graphic, showing what are the variables that are putting more energy into that deviation. So you can start investigating that deviation. Okay. So for instance, and also we have a health index. Okay. So if the health index it's big, it's bigger than 2 in this case, we will say, okay, something may happen. And you go to we create an alert. You go to that alert and you see, okay, oh, the power consumption is higher than usual, and maybe the pressure inside the lubrication system is lower or higher than usual, a temperature, whatever. Okay, so you can start investigating that. Okay, so that's a summary of the alerts that we implemented for this solution. Um, as you can see, 4 main equipments: primary crusher, the feeder system, conveyor belt that it's called the sacrifice conveyor belt, and a regenerative conveyor belt that it's an overland conveyor belt that take the ore from the primary crusher to the plant. Okay. And well, this is just a couple of screenshots of the system, how you can see the fault tree, how you can monitor the system, like the main variables or alerts with this tree map. And um, we've been lucky in this case. Because nothing wrong or nothing bad have happened to this plant. So it, at this point, it's like an insurance. Uh, but last winter, we saw something interesting. So last winter in Chile, this plant is in the Andes Mountains. There were a lot of snow. It was like an old school winter, and we started seeing this deviation. Okay, what happened? And well, it turns out that the lubrication system was giving like an acknowledge of this harsh winter, and that was the reason of the deviation. Nothing to worry about, but it shows you this type of things. Okay. Okay, and to start finishing my part of the presentation, I want to share with you the last use case of technology infusion. In this case, it was inside this asset performance management solution, and we mainly infused it with first principle digital twins. But for a slightly different use case, the main challenge that this customer has um, was they wanted to do what if scenarios. They wanted to do what if scenarios, and let me show you. They have this roasting plant that goes after the concentrator plant. And the main objective of this roasting plant was to take out the excess of arsenic that came in the copper concentrate. And for that matters, they had to roast it, and they can separate and produce calcine in this case. And so what happened with this is that we're a little blind on what was going into the roaster. So they have this nice dome where they were stocking the copper concentrate. Uh, they have this stacker and reclaimer, and they were doing laboratory measurements, but before the stock. So when they were reclaiming, they didn't have a real-time way or a nice way to understand what they were reclaiming, what were the properties of the ore that they were reclaiming. So we created one model in Python for the dome, um, that it's mainly this. data structure that can help the process engineer to understand what they are reclaiming. Okay, so when we stack, we also stack in a way the data of the laboratory analysis, and then when they reclaim, they can reclaim that. And in the roasting plant, we did a Unisim model with high fidelity thermodynamics for it. Okay, so this is the dome model. You can see more or less the idea. It works wonderfully because it's a fine dome. You don't have the segregation that you may have after a primary crusher. Okay, and as I said, it's the main idea of this model is to have this data structure where you can, when you are reclaiming the mineral, you can reclaim the laboratory data in a way. Okay, and this was the roasting and gas train simulations in Unisim, and everything was integrated into our asset performance management solution class. We created this customized user interface. It was a web application where the process engineer in this case can monitor the calculated information that came from the simulation and compare in some cases with the real measurements in the process. Plus, they had the chance to do what if scenarios. What if I reclaim from this part? How will behave the roasting client? And at this moment, we are also implementing optimization routines to generate recommendations on where to reclaim to maintain a steady operation. Okay. Plus, we're using some of this information that we're calculating with this digital twin to feed forward some extra information into the advanced process control. So there's another role there for process optimization. Okay, so we're reaching the end, and I want to share with you some closing remarks. Okay, so how we can enhance neural processing. The idea of technology infusion is super powerful because uh, the end game is not to reinvent the wheel. There are things that are working wonderfully. We've been using PID loops for a long time, and we don't plan to replace them with machine learning. We may infuse some machine learning to tune them online, to adapt them online. Okay. We have the goal, the end goal of move from control to autonomy. Okay. We want to have autonomous plants that are more resilient, that are fault tolerant. Okay. We know that one of the key elements for that is the intensive use of simulation. And we've been working hard to tune those simulations. The exact word is to reconcile those simulations with the real-time data to match the reality. Okay, so we can have this digital first solution with the digital plan is taking the lead in front of the real plant. Okay, and we want these intelligent solutions that give us real explainable recommendations. You know, we don't want more black boxes. We want intelligence that is actionable. So we want to trust in those models, and for that matters, we don't need, as I said, black boxes. And now Cesar will share some closing remarks and a call to action also. Bye.
Thank you very much, Rodrigo. Yes, just to close, as you could see during the presentation, we have a very rich and complete portfolio of solutions based on AI to support metals mining and minerals processes, mineral industries. So not only based on technology or techniques, but also based on the experience that we have in the field for many years implementing solutions for this industry. So if you want to engage with us, to evaluate, to implement the solution that we just described in this presentation. There are many touch points, there are many ways to do it. So can be a typical technology implementation program, right? A project that we can implement in your company, but can be also the implementation of a pilot test in one particular area of your company, a proof of concept in one unit, or even a co-development, a co-innovation program. So all those possibilities are open. So the way that we do in general is we have an initial engagement, typically is a meeting or in a better way, a site visit, a workshop with all the incumbents with the process, so we can identify what are the pain points, what are the priorities, and what are the typical use cases that you want to address. And then once we identify those priorities, we define what is the best way to continue. Again, can be from a POC, pilot, technology implementation to a co-development program. So in all that spectrum. So first thing is, let's get in contact. So my email and Rodrigo's email are in the last slide of this presentation. You can contact us. Please don't hesitate to contact us directly. But you can go also to your account representative. We have an account in all of your companies, so you can go and contact them, and they are going to reach to us, and we can then program these visits. So it has been a pleasure presenting today our technology portfolio. We are eager to hear from you and to start collaborating. Thank you very much.
All right, gentlemen, that was a lot of great information. I'd like to extend a big thank you to both of our speakers, Rodrigo and Cesar, for your time and expertise. I'd also like to extend a special thanks to the sponsor, Honeywell, for sponsoring today's event. Finally, on behalf of Control Engineering and WTWH Media, thank you for joining us, and we'll see you again at the next education session. Goodbye, and have a great day.